Hi everyone. Today we're going to be talking about exponential growth and decay. So we're going to be focusing on everybody's favorite today, word problems. Our only objective for today is to solve problems involving exponential growth and decay. So let's start with exponential growth. So exponential growth occurs when some quantity or some number increases by the same rate over some time period. So by the same rate over some time period. And the general form of exponential growth looks like this. Y equals A times the quantity 1 plus R to the T. So what do these stand for? Well, Y stands for our final amount. So that's what we're going to end up with after some growth rate over a specific time. A is going to be our original amount. So original amount. R is going to be our rate of growth expressed as a decimal. So rate of growth as a decimal. So what I mean by that is, like, if you had 20%, say 20%, the decimal of 20% is 0.2. We want that guy. We don't want the percentage. So if I have a 20% growth rate, that's 1 plus 0.2. And T here stands for time. So let's see this in action. Let's do an example problem. Okay, so we're told that a painting has an original value of $1,400. And we're told that the value of this painting increases by 9% each year. Write an exponential growth function to model this and find the value of the painting in 25 years. Okay, let's start with first things first. This is our equation that we want to model it after. So we're going to have to define a few variables here before we can go further. So y is the thing that we're trying to find. We don't know y. Y is our final amount. So a is going to be our original amount, and we're told what that is, $1,400. So a is going to be $1,400. R is going to be our rate of growth expressed as a decimal. So we're told that our value increases, or its growth rate is 9% each year. So 9% in decimal form is 0.09. So that's R. Now we can write a function for this. We don't have to know T because we're not really evaluating anything yet. We're just creating a general function. So here we'll have y equals A, so 1,400, times 1 plus R, so that's 1 plus 0.09 from here to the T. And we don't know what T is yet. In other words, we can simplify this a little bit. Y equals 1,400 times 1.09, that 1 plus 0.09 to the T. That's our function. First step done. Now we have to find the value in 25 years. Here is where we're going to be plugging something in for T. And as you might guess, T is going to be 25 for 25 years. So we're going to plug this in. We're going to get y equals 1,400 times 1.09 to the 25. And when we multiply this out on our calculator, we'll get that it's going to be $12,072.31. That's a lot of money. All right, on to exponential decay. Okay, exponential decay is very similar to exponential growth, except instead of going up, we're going down. So exponential decay occurs when some quantity or some number decreases by the same rate over some time period. So it decreases by the same rate over some time period. So the equation for this, the general form, looks so similar to the exponential growth one. There's only one small difference. So we have y equals A times 1 minus R to the T. So this minus is the thing that's different. All right, so what do they stand for? Same thing as before. Y is going to be our final amount. A is going to be our original amount. And R here is going to be our rate of decay expressed as a decimal. So rate of decay as a decimal. And t is going to be time. So really the only difference here between exponential growth and exponential decay is that we don't have a number over 1, we're going to have a number under 1 in these parentheses. So we have a minus instead of a plus. All right, let's see this in action. Okay, here's our second problem. The population of a town is decreasing at a rate of 1% per year. In 2000, there were 1,300 people. So we want to write an exponential decay function to model this, and we want to find the population in 2008. So let's work on creating a function here first. We have y equals a times 1 minus r to the t. So we have to define a few things here. Y is what we're trying to find. That's our final amount of people, number of people. We don't know yet. A is our original number of people. So that's 1,300. R is going to be our rate of decay. So the population is decreasing at a rate of 1%. So that's 1%, but we need it as a decimal. So 1% is 0.01. Now we can plug this into our equation here, and we'll find that we have y equals 1,300 for A times 1 minus our rate of 0.01 to the t. And we can simplify this. We'll get y equals 1,300 times 0.99 to the t. This is saying that every consecutive year will have 99% as many people as the year before it. So now let's evaluate what the population would be in 2008. Be careful here. We can't just plug in 2008 for t because we started in 2000. So if 2000 is like our 0 mark, then 2008 is going to mean that our t has to be 8, because that's 8 years after we started. So t equals 8. And when we plug this in, we'll get y equals 1,300 times 0.99 to the 8. And this is going to give us a number that is so slightly below 1,200, but we have to round up because we can't have fractions of people. So we're going to have 1,200 people, and that tells us that we had 1,200 people in 2008. All right, our last topic has to do with exponential decay, but it's a special kind of exponential decay, and it's called a half-life. You may have heard of this before in science because it comes into play in chemistry and physics and even biology. So a half-life is basically a way to express how some radioactive isotopes lose their radioactivity. So a half-life is the time it takes for, you guessed it, 1/2, so 1/2 of a substance to decay into another substance. So the formula for this looks very similar to an exponential decay function, but we have a few new variables here. So we have A equals P times 0.5 to the T. A, just like before with our Y, is going to represent our final amount. So our final amount of whatever substance we started with. P is going to be the original amount of that substance. So original amount, just like before. Now the thing that we're missing in here, we used to have a variable in here. Where'd it go? Well, our rate of decay is always 50%. That's why we call it a half-life. So 1 minus 0.5 gives us 0.5. That's where that number comes from. And T, just like before, represents time. Now I'm not going to go into an example problem here, just for the sake of time, but we will explore this in class tomorrow. All right, thanks for watching. Try those problems, or actually it's only one problem at the bottom of your guided notes, and I will see you soon.